So I remember about 2 years ago giving a talk on GPU Direct, the very first version, here at this meeting. And since then, a couple of things have changed. One thing is the GPU Direct has evolved. There has been a lot of co-design done by NVIDIA together with Professor D.K. Panda's group. So if you saw his slides, most of the material he presented is kind of here, but I also have some Intel MPI results. That brings me to the second topic, because when we presented those results, the HPC accelerators at that time were only NVIDIA's, but now we know we have mics or KNCs or Xeon Phi, whatever you call them. So I would like to give a user level view, people who are targeting these devices for HPC Center, why do they care about doing MPI directly outside these accelerators? What are the problems and challenges? And what solutions are out there right now and today? So before we get started, since I'm presenting two systems together, so I thought it's good to get like a canonical view, what our node looks like from a user point of view, from a application programmer point of view. We have a multi-core CPU, all we know. We have some memory, and we connect it through a memory channel. Then we have some network connection. Now we bring up an accelerator next to it to accelerate our computation. We attach its own private memory, connect two things together through PCIe. So this is, when a user goes onto the system, on a hybrid system, this is kind of the picture they try formulating in their head. But the important thing is to put numbers against these boxes. And that's where things start getting a bit more interesting. We know roughly today for a one-socket system, depending on range of frequency, you can get roughly between 100 and 200 gigaflops on a x86 CPU. This number is much more impressive on a GPU side of things. And here I'm considering even the latest NVIDIA system, which can get you maybe close to this number, the Titan card. Then we start looking at memory. Typically, okay, on HPC system, we don't put 256 gigabytes, but we can put 32, or that's fairly common. But on the accelerator side, the dedicated memory is rather scarce, if I can say so. Another important consideration from a programmer point of view that comes in, how quickly can I read things in and out from the memory? We have this number if you consider any DDR3 technology. But this number is rather big if you consider GPU memory. So just by looking at it like here, you can see there is kind of a loop-sided view of the world. We are gaining a lot by our factor of 2 on one side, but then we are losing out a lot. Ideally, we'd like to have everything everywhere, but because of technological issues, it's not feasible. And if we want to communicate between the two worlds and outside the world, we have QDR or FDR bandwidth and bandwidth in between the two. So one may ask a question, okay, we know very well how the CPU world works. Applications have been tuned and optimized for it. We have good network, Mellanox. Why do we really care about getting an accelerator in our system to get our lives complicated? The answer is this. You get some performance out by spending so much in your power bill or energy bill. But on the other side, you just multiply by roughly a factor of 2, but you get a lot more out in terms of floating point operation performance. And that is the main motivation for big HPC center to extract power, to have these devices to make lives complicated for end users. There. I mean, there is some cost benefit, but we are not really going to talk about it. So what we are going to do, talking from an MPI point of view, is how it would change MPI, or in some cases I/O requirements, when you can do a lot of work, one versus the other, but at the same time you have this constraint of less memory on the other side versus more memory on the other side. And that is roughly the picture if you have in your head. This is the system. The balances shift one way or the other on these devices, and how I do MPI and why I do that. So I will give you some application scenarios. So the very first application scenario is I have a data structure. Let's consider it is a 2D data structure, a matrix. And because my GPU is so powerful, I want to compute this thing on a GPU. I can do whatever I do very quickly, but at some point, I would like to communicate some halo regions, which is very common, to a GPU which is sitting over the network or remotely. So I need to be able to transfer not the whole data, but some data relative to my whole data structure. The other scenario is like this. You could have a lot of small data structures packed together, but at the same time you have this requirement, I probably need to transfer relative to the data structure that sits on my memory, like on GPU memory. So not always you always transfer a very small fraction of data that you have on the GPU, but there could be some situation where you would probably transfer a larger fraction of your data on the GPU. Now situation is, as the GPUs and the hybrid programming is evolving, we have other scenarios where we are using a high-level programming language like OpenMP in some cases, or OpenACC, this new accelerator directive space language. What happens there is when someone uses CUDA or OpenCL, you explicitly declare your intention of, okay, I'm taking data onto the host, or from host to GPU, and GPU to host, and then I do MPI. So it's a very structured type of workflow from a programmer point of view. But once you start writing a high-level language where you really do not declare explicitly when data goes in or comes out of GPU memory from CPU memory, then you would write MPI send or any other MPI calls where it may be possible that your data is already on the GPU and there is no benefit for transferring it explicitly on the CPU, and you can gain a lot by having an accelerator or GPU-aware MPI. There is a fourth scenario which is only applicable to Intel Xeon Phi, and those of you who know would realize it very easily. So in case of Xeon Phi, we have a CPU and a GPU. And Intel tells us, you can spread out your MPI all over the place, which is good. They call it asymmetric mode. But the question is, knowing the relative performance, frequencies, and capabilities of those two devices, and the communication overheads between them, how do you load balance it? So in order to be able to do that, you really, really need to understand quite well how your MPI is implemented, whether it's implemented efficiently for your heterogeneous system, and you at some point need to benchmark it. You need to understand some numbers if you really care about getting some performance out of more than one node. So throughout this talk, I would go back to some of those scenarios and present some numbers. But just to summarize, so the motivation for us as users is, and the motivation for this work we have been doing is, we want to really understand and optimize and tune for small message transfers. Small means around 1 kilobyte or less. We want to be able to then get the best efficiency out of large messages while working on these vector accelerators. And we want to know if you have multiple heterogeneous systems, and all of them communicating with each other, the system doesn't choke once you implement accelerator-aware MPI, because you will end up doing some collective operations. Or the other motivation for us and many users are, when I don't do explicit transfers, can I rely on my MPI? The same way now we know an MPI is SMP aware. So if I'm on a node, I just do a mem copy. I don't go through the whole network stack. So we want to have the same feature for accelerators and GPUs. And the final part is, doing this work was we wanted to really identify, is it really worth programming in asymmetric mode for really anything on Intel Xeon Phi? So this is our first test system. Again, a very high-level view, and just as a summary, it is 2 Sandy Bridge socket, FDR interconnect, two NVIDIA Kepler GPUs, and it's roughly connected like that. Our second system, which is an older system, it is a QDR system where we had 2 Fermi devices and 2 Intel Westmere. It is an iDataplex system. The connections are slightly different, and they do show up in some results, but not by a whole lot. So now, before we go to GPU numbers, we just want to have a reference what we get between 2 hosts on a network. So I created some little animation for you. So if you have 2 multi-core CPUs on a QDR network, and I transfer packet back and forth on QDR, for an 8-byte message, I get roughly 2 microsecond latency, and I'm just referring to some latency number and some bandwidth number, and they change a lot in between, but you will get an idea. So it's roughly like that, and roughly 3.2 gigabytes per second on a QDR. I do the same thing over FDR, and of course, now I'm much faster. In fact, it goes about 6.4. QDR 8x. So now these are my reference number. The reason I present these here, because you can easily then do the math, what changes on both systems when I try doing it between GPUs. Because between the hosts, this is what I'm capable of doing. So now I'm not going over the network. It is on a single host. And I sent this message over PCIe from a Westmere to a Fermi. So this is on-node number I get relative to those 2 microsecond, around 10 microsecond latency. And then my bandwidth numbers are around 5. It's like over 5, but with MPI overhead. These measurements are all done using MPI. Nothing is done using any low-level library. So whatever MPI overhead, you can see maybe better number just using some low-level test. I bring in an Intel Sandy Bridge and Kepler, and as most of you know, the Gen 3 is not enabled there by default. So my latencies, I think it's merely because of the frequency reasons, goes down, but not by a whole lot. But I see the bandwidth going up. I think there is something wrong there. It's not 8 gigabytes. It's about the same. So what do we do when we get over the network? So when we go over QDR network, if I do transfer from one GPU over the network to another GPU, my latency is almost doubled. If you remember from previous slides, it goes from 10 to 20 microseconds. But in terms of bandwidth, because the way it's been done implemented in MPI, I sustain almost all of the bandwidth that is available between the host. And then when I start doing it on my new system, FDR with Kepler, I see a little bit gain, and I see bandwidth going a little bit higher. In fact, it's less than 6. I get about 5.7, but I just rounded it up. But the important thing was to see where the bottlenecks are. Previously, when we had that system, the bottleneck was QDR with 3 gigabytes MPI latencies. But on the new system, the bottleneck has shifted. It's shifted between the host and GPU transfer, which really limits it, and where it cannot see the whole bandwidth. That's why we were very, very interested in getting Gen 3 capability, which we currently do not have. So this is, I didn't want to present too many results, so that's why I just picked up one. It is an MPI all-to-all I used, and then I measured bandwidth by running it on 4 nodes, each with 2 hosts and 2 accelerators. So in total, there were 8 MPI tasks, and we did the task binding such that 1 host and 1 GPU, one MPI runs on 1 GPU, if you want to think about it like that. So we really wanted to see, okay, up until now, we were doing point-to-point simple test. What if we just flood the network where GPUs to GPUs are transferring message just like crazy, which is what you would expect using MPI all-to-all. And I don't have host numbers here because they would rather change the reading here. But you can see the extra bandwidth available. The thing I wanted to show here is this extra bandwidth available on the network side, in this case, really shows. We know the bottleneck has shifted going from network to between host and GPU, but you can see that on the QDR and Fermi side, as we start increasing message size or straining the network, we are probably straining more the network that is between host and the device than the network, the FDR network. So we are really, really limited by, in this case, by the Gen 2 bandwidth that exists between host and the device. So all these tests are I think now, we modified some of those Ohio State and other benchmarks to run these tests, but I think now they are probably available through Ohio State benchmark suite. And if you have a cluster like this, I would encourage you to try out and see. First of all, first thing you learn is how you bind your MPI and GPUs, and then second thing you learn is, okay, if there is a problem in the network, or there is a problem between your host and the device connection. So we are still, these results were collected a couple of days ago, and we are still sort of learning and doing things. But we were kind of really surprised seeing such a big gain on the FDR, on the Kepler cluster. So just to summarize, what do you need to know? Go and get yourself MVAPage. We figured out, for the most part, there is this GPU capability available through OpenMPI, but for the most part, on InfiniBand system, it worked out just out of the box. You build it, and it usually works. The other thing I want to highlight, as I mentioned very, very at the beginning of my talk, I gave a similar talk 2 years ago where we just talked about how you set up GPU Direct to work. But since that time, GPU has evolved a lot, GPU Direct. And on exactly the same hardware, the latencies at least have been halved. So, okay, on the new system, we get better bandwidth numbers. But if you have if you have a 2-year-old hardware, for example, just with the software driver and changes and NVIDIA introducing 2-feature IPC and this unified virtual address space, you can see a factor of 2 improvement from those early days. So I went back and I checked my results that I collected about 2 years ago, and I said, oh, doing nothing on the exact same hardware, we gained a factor of 2. So if you had bad experiences some years ago, I would encourage you to try it again. The bandwidth improvements are there. But if you want to really, on an FDR system, if you want to really see this very high bandwidth, 5.7 or 8 gigabytes per second, you have to set an environment variable where you increase the buffer size. By default, you don't see that. So if you are interested, make sure you run your experiments doing that. The other thing we found is all these experiments are highly, highly sensitive to the version of driver you are running. If you happen to have a wrong version of driver or some wrong setting in your driver that could influence your PCI bandwidth, you will not see this type of performance. The best thing to do is maybe do some latency tests first, because that's where you really see the performance loss. So just don't take things out of the box as is. You have to maybe do a bit of a homework. Other thing is important, again, it's pretty much problem dependent, but if you are really doing a bandwidth sensitive test where you are stressing the bandwidth, make sure you have done the right binding on the system. There are multiple ways of doing this binding, and you can find details, I think, elsewhere easily. There are other miscellaneous options which you may, if you are interested, you would care about, but you can find it online elsewhere. Now let's move to our Xeon Phi. It's almost it's in fact identical system as our Kepler test bed. The only thing difference is rather than having two Keplers, in this case we have two Xeon Phi, and it's the same FDR system and same Sandy bridge and everything. What I've been told to insist that the software stack we are using on this system is beta, although hardware is GA, but so results can improve or whatever can happen if Intel changes to decide once they release the proper software. But this is what we have. So unlike the results that Professor Panda presented yesterday, all my results are collected with Intel MPI. So that's the only difference, but the numbers are about the same. So again, now we do the on-node stuff. We have on-node a Sandy bridge and a Xeon Phi connected with the Gen PCIe Gen 2 connection. Again, the usual stuff. We send packet back and forth. And on-node, the latency is, I was quite impressed, because if you remember, for Kepler and Sandy bridge, it's roughly 9 microseconds for that message size. And the bandwidth numbers are also about the same. So far, okay, good latency and about the same bandwidth compared to Kepler. As we know, on an Intel mic, you have a mic can be considered as a CPU. In fact, you can have 2 MPIs running on 2 cores just on mic. So for the asymmetric mode where you can have more than 1 MPI task, we wanted to know how much is the bandwidth and latency there. So we said, okay, how about if we do the message transfers on the mic itself? And it was, again, mic has a very low clock, so it's not considerably different compared to doing it between mic and the host, because they have this spatial SIFT protocol. But it was around 3 microseconds. Okay, bandwidth was rather quite poor. We cannot do this measurement on a Kepler because you cannot launch an MPI directly there. So we knew that for the most part, if someone were to divide up the problem between mic and Xeon Phi, for bandwidth related issues, bandwidth sensitive problems, they will have an issue. Then we said, okay, what happens when we start sending things over the FDR network from one end to the other? Again, the packet going from a core of mic over to FDR to a core of another mic on another node. So the latency double. So, okay, you can do the math. But the bandwidth turned out to be, I mean, it dropped quite significantly compared to what we saw, which we saw just on the node system. I tried confirming this with Intel, and they said, I'm seeing probably the right number. So, and I think Professor Panda also probably saw a similar number on his system. So as I said earlier on for Kepler, I think there will be a lot of hardware-software co-designing going on. So I won't be surprised a few months from now, these numbers could improve just with exact same hardware. But we'll see, we'll test it. The biggest surprise, or I would call it a shock maybe, when I tried contacting or touching a mic that was where I had to go over the QPI link, there was an impact on latency, more than the QPI latency, but the bandwidth was really, really poor. So you could just imagine that rather than sending to my data to mic 0, now I'm sending to data to mic for which I have to go over QPI network. And if I do MPI that way, just on the host, I can hardly tell the difference. So there is apparently a bug in the implementation of the software stack that does the memory sharing between mic and the CPU, and it's probably specific to QPI, so they will have to fix it, because this is not what would you expect. And knowing these numbers, I think the asymmetric mode really does not make a lot of sense. So if you are interested still in terms of repeating these experiments or doing some of your own, what do you need to know? Again, like if you work with bleeding edge technology, you always are patching and finding bugs and fixes elsewhere. So before you give up, or before you say, why my numbers are so bad, just go to a MIC forum or elsewhere and just double check whether you have all components of your software stack in order. And there are several components. I'm not going to tell you what they are, but we found ourselves that some of these can really make a whole lot of difference in terms of what you can run to begin with, and then what you see in terms of performance. This is kind of interesting. In some cases, depending on your background, it's rather intuitive how you specify how many MPI I send to mic and how many MPIs I send to the host or binding. But I think we will probably make it easy, but right now you can end up writing a very long line just to do a 4 MPI task experiment. But make sure you know that, because otherwise you will be reading the wrong thing. I tend to ignore warning messages most of the time, because I usually work with very early software stack, and warnings are okay, whatever. But in this case, when I realized some warning messages made 2 orders of magnitude difference. So if you are having problem, maybe it's worth looking at some warning or paying attention to a little bit to the warning messages. That's what I found. The other thing is, again, it's also work in progress. What I found was that the direction in which I do my MPI launch or process management can change a lot in terms of performance. It doesn't happen on CPU side, but it really does happen on Xeon Phi. But so the idea is, if my first MPI is on the host and sec task 0 versus task 1 on Phi, and I reverse the order, I may see slightly different, or in some cases considerably different numbers. So this is something we are still investigating, and there is no plausible explanation. I think it should be fixed, and it could be fixed and will be fixed. But this is something, so the numbers I showed you are the best number with a proper affinity, but this can also matter a lot. So what do we do next? We saw some early results Professor Panda presented yesterday with GPU Direct RDMA. But what we really, really want, because to me, we are technology agnostics. So whether we have a mic as an accelerator or a GPU as an accelerator, what we would eventually like to have a consistent MPI for users, which is aware of B-mic. I wrote it GPU, but I really meant a consistent accelerator-aware MPI, which know the bindings, which can see, okay, if my GPU is on the same node, I can do better transfer. I mentioned this thing, I think, 2.5 or 3 years ago, and finally it looks like it's coming. But again, it's in a very controlled environment, so we'll see when we get it on our systems. But I'm looking forward to giving it a try. This is another interesting question, because if, for example, once we start using Xeon Phi like a GPU offload type of mode, do we need an MPI that aware where we don't know? No one told us anything, but this could be very important as well. Then final part is, okay, what if I want to open and close my files there or write a lot of data? We haven't done any work there, but I'm really interested if this, first of all, makes sense, and if it does make sense, what are the challenges there? You can find pretty much everything on these pages. So you'll have the slides. And we work very closely with Professor Panda's team on these clusters they have access to, and we got a lot of feedbacks and fixes from them. And as I said, this is some bleeding edge hardware. So at CSCS, we all, system administrator, ourselves, benchmark, we work together to get the results, the results I showed here. Sometimes it could mean there is 3 to 4 weeks of work behind just to get some of those numbers. And then also I would like to thank vendors for openly exchanging info. So this is my last slide.